Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is timers executing the cumulative on-delay function. Our objective is to introduce the cumulative on-delay function and put it to use in some illustrated examples. This lecture operates under the assumption you've watched all the previous timer functions lectures, all available at the Big Bad Tech channel. If you haven't watched these lectures yet or only dimly recall their contents, please take the time to do so now. Those of you that have been following the timer functions collection closely will be absolutely overjoyed to learn that the cumulative on-delay is the last of the general timer functions I intend to discuss. From this point on, we will make regular use of these general timing functions. However, I may introduce subtle variations and manufacturer-specific intricacies. If at any point you need a refresher on a specific general timer function, these lectures will always be available for you to revisit and review as needed. Recall that a timer is a control device that exhibits a time-based shift between the assertion of its controlling input and the activation or deactivation of its associated contacts. Timers can perform numerous functions, including, but not limited to, on-delay, off-delay, on and off-delay, flash, repeat, or recycle, positive or negative edge-triggered one-shots, cumulative on-delays, and more. Today's lecture deals exclusively with the cumulative on-delay function. A simplistic timing diagram of a timer executing the cumulative on-delay function would look like this. A cumulative on-delay, as the name implies, keeps track of accumulating discontinuous assertion of the controlling input. Only after the controlling input has been asserted for the predetermined period of time, continually or discontinuously, do the outputs respond and change states. Before we dive into an in-depth discussion of the cumulative on-delay function, allow me to perform a brief walkthrough and review of other common timing functions. My intention in doing this walkthrough is not to confuse you, but rather to compare and contrast their behavior with one another. Repeated exposure to this topic is the best tactic because similar terms are employed for different functions, and it'd be a horrible mistake to confuse one function for another. Expect me to revisit this exact same walkthrough of common functions every time we have occasion to discuss a new one in depth. Recall that a timing diagram of a timer executing the on-delay or delay-on-energized function would look like this. When the controlling input is energized at this instant here, the associated contacts do not instantaneously switch to their opposite state. The normally closed time-open contact remains closed, and the normally open time-closed contact remains open. Only after the predetermined delay period T has elapsed do the contacts change states here. The normally closed time-open contact opens, and the normally open time-closed contact closes. When the controlling input is de-energized here, the associated contacts quasi-instantaneously revert to their normal deactivated state. The normally closed time-open contact recloses, and the normally open time-closed contact reopens. The on-delay timer could be used to turn another motor on a measurable time period after another has started. Compare this behavior to a timer executing the off-delay function. A timing diagram of a timer executing the off-delay function, sometimes called a delay-on-de-energize or DODE, would look like this. When the controlling input is energized at this instant here, the associated contacts quasi-instantaneously switch to their opposite state, just like a regular control relay. The normally closed time-closed contact opens, and the normally open time-open contact closes. However, when the controlling input is de-energized here, the associated contacts maintain the asserted state. The normally closed time-closed contact remains open, and the normally open time-open contact remains open. Only after the predetermined delay period T has elapsed do the contacts revert to their deactivated state. The normally closed time-closed contact recloses, and the normally open time-open contact reopens. Note the different terminology and schematic symbols employed by the off-delay in comparison to that of the on-delay. They're opposite, as one would expect. An off-delay could be used to keep one motor running for a measurable period after you turn another one off. Note for this general purpose orientation, I've purposely simplified the timing diagram of an off-delay timer. Compare this behavior to a timer executing the on and off delay function. A timing diagram of a timer executing the on and off delay function would look like this. An on and off delay, as the name implies, executes a combination of the on delay and off delay function. When the controlling input is energized at this instant here, the associated contacts do not immediately switch to their opposite state. The normally closed contact remains closed, and the normally open contact remains open. Only after the predetermined delay period T1 has elapsed do the contacts change states here. The normally closed contact opens, and the normally open contact closes. This is the on-delay portion of the on and off delay function. When the controlling input is de-energized at this instant here, the associated contacts do not immediately switch to their opposite state, but rather maintain their activated state. The normally closed contact remains open, and the normally open contact remains closed. Only after the predetermined delay period T2 has elapsed do the contacts revert to their deactivated state. The normally closed contacts reclose, and the normally open contacts reopen. This is the off delay portion of the on and off delay function. A symmetric on and off delay timer means the on delay and off delay time period are equal to each other. T1 equals T2. To set a symmetric on and off delay timer would necessitate only one delay adjustment. In contrast, an asymmetric on and off delay timer means the on delay and off delay are not equal to each other. T1 does not equal T2. Timers executing an asymmetric on and off delay would require two independently adjustable delay periods. An on and off delay timer could be used to coordinate two motors such that motor B stops a period after motor A starts, then motor B stops a period after motor A stops. Note, for this general purpose orientation, I've purposely simplified the timing diagram of the on and off delay timer. Compare this behavior to a timer executing the flash function, sometimes called repeat or recycle. A timing diagram of a timer executing the flash function would look like this. When the controlling input is energized at this instant here, the associated contacts continuously alternate between the activated and deactivated state with a measurable period. Similar to our previous discussion about on and off delay timers, flash function might be symmetric, where the activation period is equal in magnitude to the deactivation period, or asymmetric, where the activation and deactivation periods are independently adjustable. A symmetric flash would necessitate only one adjustment. In contrast, an asymmetric flash would necessitate two adjustment points, one for delay period T1, one for delay period T2. The flash function could be used to create a super annoying warning strobe when a motor is energized, or perhaps timeshare a load between two different motors. Finally, compare this behavior to a timer executing the one-shot function. A timing diagram of a timer executing the one-shot function would look like this. For a positive or rising edge triggered one-shot, when the controlling input is energized at this instant here, the associated contacts only temporarily assume the opposite activated state for a period T, and then revert to their deactivated state, despite the controlling input still being energized. This would be a rising or positive edge triggered one-shot, and essentially does exactly what the name suggests, and that the one-shot function is only enabled once for a period T on a rising or positive going transition of the controlling input. Alternatively, a negative or falling edge triggered one-shot is one that the one-shot function is only enabled once for a period T on a falling or negative going transition of the controlling input. One-shots can be used to assert an output for a desired time period following the energized or de-energized transition of another device. One-shots are particularly interesting because manufacturers occasionally include a slew of handy features, including resets and retriggerable versus non-retriggerable one-shots. Note, for this general purpose orientation, I've purposely simplified the timing diagram for rising and falling edge one-shots. To be sure, there are other timer functions and twisted offspring of unholy unions of these common functions. However, these are more than likely the most common timer functions you'll run across. This orientation is intended to be general in nature and does not dive into specifics nor manufacturer idiosyncrasies. Be aware of subtle differences in different terminology used to describe the same features. While this timing diagram illustrates the cumulative on-delay function in its simplest form, the truth of the matter is that not all cumulative on-delay timers are this simple. Being solid-state devices, the microchip conducting the timing operation often needs to be continuously powered up for it to execute the cumulative on-delay function. The internal circuitry of the microchip will be responsible for keeping track of how much time remains in the bank and how much time has been spent. For this reason, timers executing the cumulative on-delay function often necessitate an additional auxiliary controlling input, often illustrated as a coil with three inputs, A1, A2, and auxiliary, in, or B. The coil from A1 to A2 must be continually energized for the timer to properly function. The auxiliary controlling input now serves as the initiation signal for the cumulative on-delay function, whereas the coil serves to simply power the device and maintain the running bank account. Most manufacturers refer to the bank account as the accumulator, which is totally different than the hydraulic energy storage device, also known as an accumulator, we examined in the accumulators lecture available at the Big Bad Tech channel. Ordinarily, I'd give you a link to this lecture, but it has nothing to do with what we're talking about. Accumulators in this sense mean a running tally of how long the controlling input has been asserted. If the timer is ever completely depowered, this serves to wipe the slate clean and reset the device. Note, for the purposes of this general lecture, I'm trying to avoid getting entangled in manufacturer specifics. It is your responsibility to interpret the timing diagram for your particular multifunction timer of interest. A more complicated timing diagram of a timer necessitating an auxiliary controlling input executing the cumulative on-delay function might look something like this. Given the device is powered up using the A1 to A2 terminals, only when the auxiliary controlling input is energized for a period of accumulating time more than the adjustable cumulative on-delay period do the contacts change states. Assuming the cumulative on-delay period is set to 5 seconds, and each block in this graph represents 1 second, only after 5 seconds has accumulated, hence the term, do the contacts change states. This could occur discontinuously with multiple pulses, or in one long continuous 5-second pulse. In both cases, after the controlling input disappears, the contacts immediately return to their deactivated states. I often find annotating how much time is accumulated may help in the analysis of timers executing the cumulative on-delay function. Finally, if a timer is ever completely depowered during ongoing accumulation of time, in this case 2 seconds, the accumulator is blanked out and reset to 0. When power is restored, the cumulative on-delay function would proceed as normally. To set up a multifunction timer to execute the cumulative on-delay function, a technician must first choose the correct function and then set the appropriate delay period. Here's an example of a multifunction timer with both a 2-terminal coil and an additional auxiliary controlling input. A timing diagram of this timer executing the cumulative on-delay function looks exactly as I've illustrated. If the coil ever loses power, the accumulator would be reset to 0. This particular timer can perform 8 different functions, A through H. To set this particular multifunction timer to perform the cumulative on-delay function using a period of 5 seconds, a technician would rotate the function selector to function H, the cumulative on-delay function with auxiliary, as illustrated in the table. Then a technician would choose an appropriate delay period. This particular manufacturer necessitates a 2-step process to adjust the delay period. First, select the range, then adjust the range percentage. The range selection presents possibilities from 1 second up to 100 hours. The percentage can then be used to fine-tune the delay period inside this range. For example, 50% of 10 seconds would be a delay of 5 seconds, as would be 5% of 100 seconds. However, 50% of 10 seconds would allow finer tuning around the 5-second region. Note this timer has 2 indicator LEDs, one that indicates when the device is powered up, and another that indicates when the outputs are in their activated states. Unfortunately, it does not have another LED indicating when the auxiliary controlling input is asserted. This would be a great feature, but sometimes you got to work with the tools you've got on hand. You know you set up a cumulative on-delay timer out correctly if you power up the device, assert the controlling auxiliary input for a couple of seconds, assert it again for a couple of seconds, and after an accumulation of 5 seconds of assertion, see the output change states. When the controlling input is de-energized, the associated contacts immediately return back to their deactivated states. The cumulative on-delay function seems to work just fine. Troubleshooters take note. A multifunction timer executing the right function at the wrong time needs to have the delay adjusted. In contrast, a multifunction timer executing the wrong function at the right time needs to have the function adjusted. I'd like to say that the misinterpretation of functions is a rare occurrence, but it isn't, and you need to be aware of this possibility. Let's now move on to the remaining topic of this lecture, putting a timer executing the cumulative on-delay function to use. For these examples, we'll make use of a multifunction timer that necessitates the coil be continuously powered and requires the use of an auxiliary controlling input as illustrated in this particular timing diagram. The classic introductory example of a cumulative on-delay timer is the time-delayed response of two pilot lights. Note the coil of the timer relay is continuously powered by the connection in rung 1. Opening stop would serve to completely depower the timer. Start in rung 2 serves to energize the auxiliary controlling input of timer relay TR1. Rung 3 contains a normally closed contact, TR1A, associated with timer relay TR1, executing the cumulative on-delay function in series with a red pilot light. Rung 4 contains a normally open contact, TR1B, associated with timer relay TR1, executing the cumulative on-delay function in series with a green pilot light. Let's assume the timer executing the cumulative on-delay function is set to execute a 5-second delay. Note the start state of the circuit is red light on, green light off, the timer is powered up, and the accumulator has 0 seconds. When operator presses start, the auxiliary input of timer relay TR1 is energized. If an operator presses and holds start for 1 second, then releases it, the accumulator has accumulated 1 second of a total 5-second available countdown. After a pause, let's say an operator presses and holds start for 2 more seconds, then releases it. The accumulator has now accumulated 2 more seconds. This additional 2 seconds is added to the 1 second already in the accumulator, meaning the accumulator has now used 3 seconds of its available 5 seconds. Finally, after another pause, let's say an operator presses and holds start for more than 2 seconds. This additional 2+ seconds is added to the 3 seconds already in the accumulator, meaning the accumulator has used all of its available 5 seconds, and the timer signals its associated contacts to immediately change states. The red light turns off and the green light turns on. As long as the operator holds start closed, the contacts will remain in this activated state. The moment the operator releases start, the associated contacts return to their deactivated states. We've returned to the start state of our system. Red light on, green light off, accumulator is back to 0. This circuit therefore only responds after an accumulation of 5 seconds has occurred. Importantly, the cumulative on-delay function differs from an ordinary on-delay function in that the input can be discontinuously asserted. This is pretty important and bears repetition. I say again, the cumulative on-delay function differs from an ordinary on-delay function in that the input can be discontinuously asserted. The accumulator maintains a running tally of the elapsed time. Let's now examine the reset feature afforded by this timer. Let's say an operator presses and holds start for 3 seconds and then releases it. In this case, the accumulator has accumulated 3 seconds of a total 5-second countdown. After a pause, let's say an operator opens stop. In this case, the timer is completely depowered and the accumulator is dumped. When power is restored to the timer by closure of the stop button, the cumulative on-delay begins anew and the accumulator is reset to 0 seconds. Opening stop therefore serves to reset an ongoing cumulative on-delay and clear the accumulator. Besides making some stupid lights blink, a timer executing the cumulative on-delay function can also be used to perform some industrial task. Consider a maintenance procedure that must occur periodically. For example, changing oil or a filter every 100 hours of runtime. A timer performing the cumulative on-delay function can keep track of the elapsed time and notify maintenance personnel the service needs to be performed despite the system being run discontinuously over a period of several days or weeks. Allow me to demonstrate. Rungs 1 and 2 contain a regular 3-wire control circuit that selectively energizes or de-energizes the F contactor coil, as well as the coil of a regular control relay, CR1. When an operator presses and releases start, the F contactor coil will be energized, the F primary contactor will close, and the coil of control relay CR1 will be energized. Rungs 3 and 4 contain a timer executing the cumulative on-delay function set to 100 hours. The mechanically interlocked service reset button serves to completely depower the timer and reset and clear the accumulator. Contact CR1A, associated with regular control relay CR1 in rung 2, energizes the timer auxiliary controlling input. This is the input signal that lets the timer know it needs to pay attention and keep track of the accumulating run time. Rungs 5 and 6 contain the diagnostic notification and reset circuit. The closure of either contact, TR1A associated with timer relay TR1, or CR2A associated with regular control relay CR2, also in rung 5, serves to energize the coil of the regular control relay CR2 and a red light that says Service System. Note that opening the mechanically interlocked service reset button would also de-energize both these devices. Note the de-energized start state of the system at 0 hours as the motor is off, the timer is powered up, and the service system light is off. At the start of a 10-hour work shift, an operator presses start. This energizes the F contactor coil and the coil of regular control relay CR1. Their associated contacts immediately change states. The F primary contacts close and the system springs to life. The F1 holding contact closes and allows an operator to release the start button. Similarly, contact CR1A closes and energizes the controlling input of timer relay TR1. Time in the accumulator begins to collect. Note that contact TR1A remains open since the delay period of 100 hours has not been achieved. The coil of control relay CR2 and the service system light therefore remain de-energized. At the end of a 10-hour work shift, the accumulator has accumulated 10 hours. An operator presses and releases stop. This de-energizes the F contactor coil and the coil of control relay CR1, and their associated contacts immediately return to their deactivated states. The F primary contacts open and the system grinds to a halt. The F1 holding contact opens and removes the holding circuit. Contact CR1A opens and de-energizes the controlling input of timer relay TR1. Given service reset remains closed, the accumulator now has 10 hours in the bank. Over the next several days, this process repeats itself. At the end of the second day, the accumulator has 20 hours in the bank. After 3 days, 30, and so on. Every day the system starts as previously, outwardly unchanged. However, the timer keeps track of how long the discontinuously energized system has run. Here is the system status at the very end of the 10th workday at 99.9 hours of discontinuous operation. Just prior to go-home time, 100 hours is accumulated. At this point, the timer executing the cumulative on-delay function tells contact TR1A to close. The now closed TR1A contact energizes the coil regular control relay CR2 and the red service system light. Contact CR2A immediately closes and establishes a holding circuit, thereby maintaining the state of CR2 and the service system light. An operator can now shut down the system by pressing the stop button. As previously, this de-energizes the F contactor coil and the coil of control relay CR1, and their associated contacts immediately return to their deactivated states. The F primary contacts open, and the system grinds to a halt. The F1 holding contact opens and removes the holding circuit. Contact CR1A opens and de-energizes the controlling input of timer relay TR1. Contact TR1A opens. However, the coil of regular control relay CR2 remains energized, as does the service system light, because of the holding circuit established by contact CR2A. Maintenance personnel can be dispatched to the system the very next day. The system is locked out and tagged out, and the oil or filter is changed. As part of their maintenance procedure, they press the mechanically interlocked service reset button. Opening service reset in rung 3 completely depowers the timer and resets and clears the accumulator. Opening service reset in rung 5 de-energizes the coil of a regular control relay CR2 and the service system light. Contact CR2A opens and removes the holding circuit. When service reset recloses, we've returned to the start state of our system, with the timer powered up and the accumulator back at 0 hours of service. The system can be returned to production, and after another 100 hours of discontinuous operation, the system will automatically notify maintenance personnel of its needs. In summary, the cumulative on-delay function for this circuit is acting like a record-keeping device and frees operator and maintenance personnel from this tedious responsibility. Applications of the cumulative on-delay function are numerous. However, they all generally behave in this fashion. Only after the controlling input has been energized, continuously or discontinuously, for the adjustable delay period, do the associated contacts change states. Alright, that is that for this lecture. In conclusion, this lecture took a brief look at multifunction timers performing the cumulative on-delay function. We introduced the cumulative on-delay function, reviewed general timer functions, learned how to set up an example timer performing the cumulative on-delay function, and finally employed a timer executing the cumulative on-delay function in a couple different illustrated examples. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.